It's a great pleasure to have Federica Guidi here today. Thanks a lot for accepting our invitation. Federica is a postdoc at IAP in Paris, where she is involved in the data analysis of SPT-3G, specifically for CMB primary anisotropies power spectra. She participated to the analysis of the D1 data recently published, and she is leading the preparation of the next data release with extended observations. Federica received her PhD at IAC in Tenerife, where she was involved in the KeyJot CMB experiment data release. Today, she will present precision cosmology with the South Pole Telescope, SPT-3G D1, results and beyond. Federica, please, you can start when you're ready.
Thank you very much, Eleonora, for this introduction and for the invitation to this series of seminars. So yeah, this is my pleasure actually to be here today presenting these results from the South Pole Telescope to this fantastic audience. So we have published a few months ago this first data release, this one of SPT-3G data. And this is mostly based on observations of the cosmic microwave background. So my presentation today will be structured more or less this way. I will make a brief introduction on the state of the art of CMB cosmology. It will be quite brief because I guess most of you are already experts about this. Then I will present you the South Pole Telescope and the current camera that we are using for observations, SPT-3G. And then we will dive into the results that we have published recently. And I will drive you through the analysis pipeline that we implemented from maps to power spectra to the cosmological parameters. And I will focus first on the CMB primary anisotropies of temperature and E-modes polarization. Then I will show you what we get when we combine the primary anisotropies to the lensing power spectrum of SPT-3G first, and then in combination with other CMB experiments, such as Planck and ACT, DR6. And then we will see what we can say about cosmology when we combine the CMB with BAO data, and particularly from the newest release of the DAISY experiment. And then to conclude, I will give you the future prospects of SPT-3G, what we are working on right now. So, of course, let me start with this very famous picture of the history of the universe. And what we are interested about today, and I'm particularly interested about in my research, is producing pictures the best possible we can of the primordial universe through observations of the microwaves, in which we can see the cosmic microwave background. And the satellite mission that all of you surely know, Planck, has produced fantastic images of the CMB in temperature, where you can see with very high signal to noise the anisotropies of the temperature field, and of polarization as well, which is depicted by the dashes in black from the bottom panel of this image here. And particularly, Planck has been super successful because it has been able to measure very accurately at sub% level the parameters of the cosmological model that is the standard today, the lambda CDM model, which, however, besides being super successful, it's mainly composed by dark energy in the form of cosmological constant lambda and cold dark matter. But I hope all of you agree that we actually don't know really well or well at all what's the nature of these dark components. And furthermore, in combination or comparison with other cosmological probes, we start to see some tensions on the cosmology that we can constraint with the CMB or with, for instance, supernovae type 1a, from which we can measure the expansion rate of the universe today, or from BAO, where we can measure omega m, or from weak lensing, where we can measure the growth of structure parameter S8 or sigma 8. So these tensions that we see, that are more or less significant, make us ask the question, are we seeing new physics, or is it possibly due to systematic effects? So in order to address those questions, we need more data. from different sides, and I will talk to you about what we can do, and we are actually doing with the CMB, and particularly after Planck, of course. So what we can do now is to observe from the ground, and we have two ground-based experiments that have been taking data in the last years, and these are the South Pole Telescope and the Atacama Cosmology Telescope. What we do from the ground is that we can build bigger telescopes. These are typically 10-meter single dish telescopes that can measure the CMB at smaller angular scales than what Planck was able to achieve. And we can get to higher signal to noise in polarization, which was a measurement that was noise limited from Planck data. And polarization is also great from the ground because the contamination from galactic or extragalactic foregrounds is lower than the contamination that temperature data can have, as well as atmospheric contamination from observation from the ground is much reduced when we look at polarization, because the atmosphere is mostly unpolarized. So these experiments, SPT and ACT, are providing additional and complementary information to what Planck gave us. And in particular, of course, today we will see what the South Pole Telescope is doing. And in particular here, I would like to show the kind of images that we can produce with different experiments, again, Planck, ACT, and SPT. And you can see how the maps of Planck in polarization were noise limited, while ACT is doing already a much better job measuring the small angular scales and isotropies of the CMB, but actually SPT is going to even lower noise to these small angular scale structures. So let's move now to see how SPT is doing this. So first of all, SPT, as I anticipated, is a single dish telescope with about 10 meters aperture operating from the South Pole. And it's dedicated to CMB observations at high angular resolution, typically 1 arcminute. And this is funded by the NSF and DOE. SPT is not a new experiment. It actually started observing the CMB in 2007 with the camera SPT-SZ that is depicted here, which measured for the first time the temperature anisotropies of the CMB at such a high resolution that I mentioned before. It was followed by SPT Pole that for the first time now took observations of polarization too at small angular scales. And all of this has been replaced now with SPT-3G, the third generation camera on this telescope. So SPT-3G is a huge improvement compared to previous camera. First of all, its focal plane is populated by 16,000 detectors, which is about 1 order of magnitude more than the number of detectors in SPT Pole, for instance. These detectors are organized in 10 monolithic wafers that operate at cryogenic temperatures and are sensitive to 3 frequency bands where the CMB is particularly bright, which are 95, 150, and 220 gigahertz, and achieving a resolution of 1.6 to 1 arcminute, depending on the frequency. So this camera was deployed in 2017 and is still taking data and will continue until about the end of 2027. And of course, you can imagine how many people work on installing, producing the camera, and then analyzing the data. And in particular, SPT-3G has a very wide variety of science cases. I highlighted here in bold the cosmological constraints, since this is what I'm working on, from primary CMB temperature and E-modes polarization. But SPT is also very powerful in producing lensing maps. For instance, one of the main goals of SPT-3G is indeed to cooperate with the BICEP experiment and de-lens the BICEP field to achieve possibly a detection of inflationary B modes. So I'm not gonna go through the list here, but you can see what a variety of science cases we are doing, from cosmology actually to solar system science, looking at asteroids. But what I want to focus on the attention today is what I already mentioned, but I want to stress again, is that SPT-3G dataset, thanks to the sensitivity to small angular scales of the CMB anisotropies and high signal-to-noise polarization data, and very accurate possibility to produce lensing maps, is a significant improvement to Planck when we want to constrain cosmology with the CMB. So this is what SPT-3G observes. We start looking at our main field, which is depicted in green here. This is a pretty small sky patch, about 1,500 square degrees, a sky fraction of 4% of the sky. And this footprint has been chosen to overlap perfectly with the bicep Keck field for the inflationary science purpose that I mentioned earlier. And this field is observed during the winter austral season, which is the best season to observe the CMB from the South Pole, since the sun is always under the horizon and the conditions of the atmosphere are particularly stable. So this field is observed for about 8 months per year during the winter austral season, and observations have started in 2018 after commissioning. And from a first little data set, we have already published a list of papers that you see here, and you might have heard about in the past. But what I want to talk about today is our D1 data release. Indeed, since 2019, the focal plane actually started observations in fully operational mode, and is still continue observing in these conditions today, but we focused on analyzing the observations of the first 2 years of this data set. And this is what I'll call D1 from now on. And based on this data set, we have published 3 papers recently. First, a lensing reconstruction using polarization-only data, then a study of B-mode's power spectra, in this case at large angular scales, low L. And finally, this is the newest one, the cosmology constraints from temperature and E-mode's polarization CMB anisotropies. And this talk will focus mostly on the constraints from the last paper and in combination to the lensing power spectra that we published also this year. And then there are 2 more fields that I will keep it for the end. So let's dive into this analysis of D1 data for CMB primary temperature and E-mode's polarization. So this has been a titanic work led by Etienne Campus and Wei Quan, who have analyzed from maps to power spectra for what concerns Wei, and from power spectra to cosmology from what concerns Etienne. Of course, with great help from all these people that you can see here and from the entire SPT-3G collaboration, including myself. And yeah, this is all based on these beautiful maps that have been produced for the main field. So these maps have co-added noise sensitivity of 3.3 microcalc minute, which makes of them the deepest CMB TQU maps at arc minutes resolution today. You can see here the temperature map at 150 gigahertz. So a few details about the procedure to build these maps. These are high-resolution images produced in HELPIC specialization and SIDE 8192. For our map making, we use a filter and mean approach, meaning that before combining time order observation into pixels, we actually filter the CMB at large angular scales. Indeed, these maps do not contain large angular scales information, as you might see. All these data sets, before being used for more advanced analysis, have been validated using null test in order to ensure that there were no contaminations from the sun or the moon or systematic effects by doing a number of data splits. And we can confirm that there are no systematic effects that limit our constraining power today. And I will flash now the Stokes-Q polarization map on the main field, as well as the Stokes-Q polarization map, where you can see very clearly these cross patterns that are typical of the E-modes polarization in Stokes-Q. These are the noise curves of this map. For different colors, we are representing different frequencies in temperature on the left and in polarization E-modes on the right, with coadded sensitivity quoted in red. And you can see what I was mentioning before, that with SPT-3G, we actually measure the many peaks of the E-modes power spectrum with in the signal-dominated regime up to L of about 2500. This is an achievement from this experiment. So a few more technicalities on our pipeline. Indeed, this was a lot of work to analyze such a deep data set, and we had to implement new techniques to analyze accurately and in a robust way the data. First of all, as I said, we filter our data before producing maps, which means that we remove some part of the signal. And when we do the cosmological analysis, we have to put the signal back in the angular power spectrum regime, and we do it by applying a transfer function. And this, in our case, has been accurately modeled with quick simulations produced by Ricky Vaughan. We implement a new software that can produce very, very efficiently and very quickly a large number of simulations to address this question of the transfer function. Then, for the first time for a CMB primary anisotropies analysis, we apply an in-painting technique. Indeed, our maps are contaminated by point-like sources. So radio galaxy of dusty galaxy in the sky that are point-like in the SPT beam contaminate our observations, and instead of masking them, we in-paint this location, drawing constrained CMB realizations on top of the position of these point sources. Then we rely on a software to produce semi-analytic covariance matrices of the angular power spectrum. And this is a code that the leader of the analysis, Etienne Campus, implemented a few years ago, which is very handy, and it's really great to have semi-analytic covariance matrices for this kind of analysis. And then to conclude, we have a couple of systematic effects that we have introduced as a novelty in this analysis. First one, we have been treating our beams in polarization differently from the beam of temperature, because we realized for the first time that there's the possibility that the side lobe of our beams get depolarized, and we have to take this effect into account. So we are not using the same beam for temperature and polarization. And then by the fact of masking the point sources, we introduce some artifacts in the maps that we had to model accurately and correct for at the power spectrum level, as well as temperature to polarization leakage effect at high orders that were not taken into account before, that start to become important for this analysis. So this was about low-level pipeline, but we have also a number of novelties concerning the likelihood. First of all, we rely on this very handy, differentiable and robust likelihood code called CANDLE that was implemented in the group here at the IAP by Leonard Balkenhol. We also try to speed up as much as we can our cosmology inference by using a CMB light likelihood implemented by Leonard as well. And then we use as theory codes for CMB classical Boltzmann solvers such as CMB class, but also emulators, in particular differentiable emulators like CosmoPowerJax and an online learning emulator that relies on machine learning techniques that is called OLE. And this is very helpful because first speeds up our cosmological inference, but in particular, CANDLE with its differentiable capability allow us to have a framework to perform very efficiently a large number of consistency tests. And this is very important in our case. Indeed, our pipeline is a blind pipeline. We don't look at bump powers or cosmological parameters until we pass a long list of consistency tests or null tests. First of all, we have null tests at the bump powers level that are depicted, a few examples here. The first one is a frequency difference test, meaning that we take two different frequency channels of, for instance, E-mode's power spectrum of SPT-3G, and we compute differences of those. And if the CMB is expected to be the same in the two frequency channels, and what we expect then is to obtain a difference that is compatible to 0. Similar, it's what we do in conditional tests. In this case, we fix a frequency channel, and from the other frequency channel, we make a prediction of what we expect to see in the reference channel, and we compute differences. And let me say that these tests are actually very hard to pass because they're very stringent. You can understand this concept here where we are plotting the uncertainties on the power spectra themselves in blue and the uncertainties on these consistency tests in orange and in green. And you can see that we are actually probing eventual systematics effect at a level of orders of magnitude smaller than the uncertainty of the bump powers themselves. So we are really probing the even-timest systematic. We also do null test at the cosmological parameters level. For instance, we look at inference of different parameters, looking at all our different frequency channels, and we expect that these are in agreement, and this is the case indeed. And in fact, after all this consistency test pass, we were finally able to unblind. However, life in reality is never that easy. And indeed, after unblinding, we discovered that we still had two systematics effects that were affecting our cosmological constraints and that we thought were important to model in the likelihood. And so we have had to include two unblinding changes. And these are the inclusion of the polarization of the beam side lobes that I was mentioning earlier, and the inclusion of a correction of high order temperature to polarization leakage. And you can see what these changes implied in terms of the null test that I was mentioning earlier. So these are frequency difference null tests. So for instance, our bump powers at 95 gigahertz minus the cross spectrum between 95 and 150 gigahertz. And before unblinding, we had the orange dots here that were still passing our criterion to pass this consistency test. But indeed, when we included this additional systematics effect, I mean the correction to this additional systematic effect, the consistency across frequencies improved significantly. So yes, this finally allowed us to look and use for cosmology our BAM powers, and this is what I'm showing here. These are the temperature TT cross T and E CMB and E modes, power spectra, with residuals to a model that is lambda CDM, which appears to be a very good fit to the SPT-3G D1 data set in TT, TE, and EE jointly, and also individually, as the PTs that I'm reporting here can tell you. And from a minimum variance combination of all our frequency channels, we have this beautiful CMB-only power spectra from SPT-3G D1 in blue, and in comparison to Planck in gray and to ACT in orange. And you can see how small are the SPT uncertainties, both in EE and TE at small angular scales. And this can be maybe better seen in this figure here that represents the signal to noise of these three experiments. And you can see that at scales of L above 2200 in TE and 1800 in EE, SPT has the highest signal to noise that we were able to achieve by CMB experiments. And another nice remark that I would like to make here is particularly looking at the EE signal to noise, we can see that different experiments actually peak in signal to noise in different regimes, which will allow us to probe a wide range of the spectrum of the CMB modes by combining together these three experiments. So finally, after all of this, we can see what we have to say about cosmology. And this is the fit of lambda CDM cosmological parameters from the CMB primary anisotropies of SPT-3G D1 alone. And you can see these are some parameters of particular interest. You can see the constraining power of different channels of TT, EE, and TE. We have in particular our TE power spectrum being the most constraining one, followed by EE and TT power spectra, and their combination, which is represented in black here, is obviously the one with the most constraining power from the entire data set. And just as a figure of merit, I'm reporting here some uncertainties on the H0 parameter. From SPT-3G D1, we obtain a measurement of H0 with an error bar of 1.1 kilometer per second per megaparsec, which is already a significant improvement from our previous data release, and which is not quite there, but approaching the error bars from ACT-6 and Planck, and this is only from CMB primaries for all of these experiments. However, as anticipated earlier, SPT-3G is also very powerful to measure lensing. And this is where actually a lot of constraining power comes in SPT-3G constraints. And in particular, we used the lensing reconstruction that was produced by Marius Millet and Feige, which was published earlier this year. This is a lensing reconstruction obtained with a map-level Bayesian inference approach called MUSE, which used polarization-only data of the main field of the WIT D1 survey. So these 5 power spectra, which are represented here, are the most precise lensing power spectra today at small scales, L larger than 350, which show very good consistency with ACT-6, lensing reconstructions, Planck and pipe, and as well as a model lambda CDM. And so we used our CMB primary anisotropies now in combination to the lensing power spectra that I just presented to fit cosmological parameters. And this is again a corner plot of relevant cosmological parameters today, H0, omega m, sigma 8, obtained from SPT-3G D1 data, CMB primary and lensing, and Planck CMB primary and lensing. And you can see that we actually approach this time with this combination, the constraining power of Planck, but with SPT-3G D1 alone, almost completely independently from Planck. And again, the same figure of merit as before, the error bars of H0, showing the improvement from going from CMB primaries alone to the combination of primaries and lensing. And we improve actually the constraints from SPT-3G by 45% here, and we actually exceed the precision on this parameter from the ACT dataset, and we approach the constraining power of Planck. So you have seen what has been from this data set, the results from SPT-3G alone. But in the paper, we have moved on and combined all the best state-of-the-art CMB dataset that we had today. In particular, so this is a combination of SPT-3G D1, of course, from primary and lensing, Planck primary and lensing, and ACT primary and lensing with the tau prior. And in particular, I will focus in showing the combination from SPT and ACT as what can be achieved by ground-based experiments that observe the CMB. And finally, the combination of ground space from SPT, Planck, and ACT, this SPT, CMB, SPA. And these are the cosmological parameters that we obtain from these combinations. So there are three important points to make from these results. First of all, we have seen that lambda CDM is the preferred model by the three experiments independently almost, and also their combination as a preference for lambda CDM. And this is a remarkable confirmation for this standard model from the CMB. Then from the combination of the two ground-based experiments, SPT and ACT, we can see for the first time that we actually get to, if not exceed, Planck precision. And this is really a milestone from ground-based experiments, because so far Planck results has been setting the stage for CMB cosmology, and we were not able yet to basically go beyond it. Now, from the ground, we are at the stage where we can actually go beyond what we know today and possibly test cosmological models beyond lambda CDM. And finally, from this combination of all the experiments, SPT, Planck, and ACT, we basically set the tightest constraints on cosmological parameters given by the CMB as an observable. And what we can say from this, first of all, let's start with the Hubble tension. So all the different CMB experiments measure an H0 value that goes towards low value with error bars that in combination shrink and shrink, making the comparison to the H0 measurement from the SHOES dataset more and more discrepant. So this tension is now above the 6 sigma level. So it's getting some very significant levels. And then we try to prove models beyond lambda CDM. So we will go through quickly some of the models that we've tested. So first of all, the A-lens parameters to extend lambda CDM is interesting because Planck saw a hint of this parameter to be larger than 1, which would not be in agreement with lambda CDM, but actually both ACT, SPT, and the combination of SPT and ACT have a preference for an A-lens parameter consistent to 1, so consistent with lambda CDM. Then we have extended the model with the effective number of relativistic species, NF, and with the abundance of the helium fraction. And for both these parameters, we are obviously improving error bars if we combine different CMB observables, different CMB experiments, but we still get constraints that are compatible to lambda CDM. Sum of neutrino mass, we shrink and shrink the upper limit on the sum of neutrino mass. In particular, when adding SPT to Planck, the upper limit is reduced by 30%, but we are not close to excluding the inverted hierarchy yet. And then we have tested a modified recombination model, which could be a proposed solution to the Hubble tension, but we actually find that there is a very good agreement with Planck and with lambda CDM. So again, not a preference for extensions of lambda CDM here as well. And a follow-up paper led by Ali Rida Khalife fitted axion early dark energy model. And as you can see from this plot here, there is no statistically significant evidence for axion early dark energy in the CMB. So what we did next was actually to go to a combination with BAO, because Daisy released their year 2 data recently, and it was a perfect timing to combine to our data set or with CMB in general. So here there is something to say. First of all, so we would like to combine this data set, but we need to check if actually CMB and BAO are seeing the same cosmological picture. And indeed, what has been seen here is that there is a borderline inconsistency between CMB and DESI. Borderline is in the sense that it's slightly below or slightly above 3 sigma. We set 3 sigma as our reference beyond which data sets are said inconsistent and we cannot combine them. But actually, when we go to combine CMB from SPT Planck and ACT, the comparison with DESI is at the 2.8 sigma level. And so we went ahead and we made this combination. And we actually tried to fit several extended models, and we have seen some slight preferences for models beyond lambda CDM at close to 3 sigma level. However, our understanding of this is that basically the differences between the CMB and data at the 3 sigma levels get projected into preferences to models beyond lambda CDM. And this is not for now sufficient to rule out lambda CDM, because this can still be a statistical fluctuation or some small systematic still unknown in the data before claiming that this is an evidence for new physics. So only future data sets, both from the CMB side and the BAO side, will clarify this picture. And this is what we are going to try to do with SPT-3G with extended observations, actually. In particular, I want to present here this X4K survey, which is attaching summer sky to the main field with observation taken during the summer austral season. And these are depicted in yellow here. So these observations are not as deep as those of the main field, but actually improve, enlarge the sky fracture covered by SPT-3G observations significantly, and allow us to gain signal to noise in the sample variance dominated regimes of our power spectrum. The analysis of the first 2 years of summer season is ongoing, and this is actually very close to my heart because I'm leading this analysis for 4 years now. So I'm very attached to these results. What I can do now actually is to show you some forecast. So these are actually the real results obtained from the D1 survey, what we have been seeing so far from a combination of CMB primaries and lensing. What these summer fields from CMB primary only will do are represented by the yellow ellipses here, but what we are interested about is the combination of the main field with the summer field, which builds up this next 4K survey. So H0 is gonna improve by something like 16%, which is bringing us to an uncertainty comparable, equal actually to that of Planck. But parameters, other parameters such as NS and I think omega B are going to have a significant improvement with this data set. However, what we are mostly interested about is extensions of lambda CDM. And we have seen that with forecasts, for instance, with NF, we actually improve our constraining power from SPT-3G alone by 40 to 50%. So we are going to do much better on extended model with this upcoming release. And this is coming soon, very soon. But this is not the end, because actually during last year, 2024, we really wanted to observe all the sky we could, and we added this wide field that are depicted in orange here. And this is what we call the next 10K survey of SPT-3G, because it actually covers 10,000 square degrees of the sky with even slightly lower sensitivity. But again, since we gain more sky fraction, we beat sample variance even more, and we become more constraining both on lambda CDM than to extended models. And in terms of forecast, so you can see here the signal to noise curves from TT, T and E, and the lensing as well. As a comparison, you have Planck in black or the D1 release in green, and we are going to step up with the summer fields and step up again in signal to noise with the white field. You can see from this plot and from this paper that was published in 2024 what we forecast for lambda CDM. With the white field, we expect to constrain some lambda CDM parameters by up to a factor 2 better than Planck. And for extended model, we might go in combination with Planck to a factor 3 better than Planck alone on simple extensions of lambda CDM with one parameter. And also in a paper that we will put out very, very soon that was led by Aline Vitrier, a PhD student here at the IAP, we tested how proposed models to solve the Hubble tension will be constrained with our X10K survey. And you can see how we can go from the Planck constraining power shown by the gray dashed area here to the green areas of constraints from our X10K survey. With the bonus that other than doing lambda CDM and lambda CDM extensions fit, this very wide footprint will overlap with other CMB experiments in a wide sky fraction, allowing to perform cross checks on the CMB, as well as cross correlations with other maybe galaxy surveys. And yes, this is the end of my talk. Some very briefly, I want to go through take-home messages. So you've seen the results of SPT-3G D1 from CMB primaries and lensing that confirmed lambda CDM and with compatibility with Planck and ACT. We have shown the combined parameters of SPT, Planck and ACT, which have not shown evidence for extensions of lambda CDM and which have made the Hubble tension even stronger. We have seen an inconsistency at the 3 sigma level between CMB and BAO data that gets projecting to preference to models that extend lambda CDM, but this is not quite significant yet. And we want to get more data to answer this question, and this is what we are doing. Indeed, SPT-3G D1 is only the beginning, and you will see very, very soon our results from the X4K survey, and soon after from our X10K survey. And this is all. Thank you. I'm happy to take your questions.
Thank you so much. Thank you. Very, very nice talk. Do you have any questions? Okay, maybe I can start with one. So why are you not combining instead as always supernovae data?
So this is a question that, yeah, maybe I'm not the best person to answer to. Yeah, I would not say that. I'm not sure how much the consistency between CMB and supernovae data has been assessed. To my knowledge, is probably not that consistent, and so we didn't do this in this paper.
Okay, thank you. And Paolo?
Sorry, I had to mute myself. Okay, sorry. So, first of all, very, very interesting result and discussion. And I would like just to put a small point in the fact that when you say that you confirm lambda CDM, you mean you are confirming the early time of lambda CDM. Because, I mean, there are changes in lambda CDM, especially in the dark matter content, that can be at a later time and be responsible in some sense also for the Hubble tensor. So this, I think that this is almost sure about this, but maybe to tell to at least once should be done in your presentation.
So you would treat this late time lambda CDM within still lambda CDM, because it's not clear to me if this would still be considered as an extension of lambda CDM, and maybe an extension that we have not tested here.
There are many stations, for instance, water matter scenario, for instance, that behaves like lambda CDM at the level of CMB. So there are many other variations of lambda CDM that they behave exactly like lambda CDM at, let's say, at the level of CMB, but at the level of galaxy formation, BAO or Hubble tension, they have effect, they may have some effect.
Yeah, so maybe in the combination of CMB and BAO, these other probes, it could be interesting to test this this late time. Yeah, sure. What I think I was saying is that lambda CDM is confirmed by this CMB experiment. With CMB, we basically probe the early stage of the universe.
Okay.
Indeed, when we start combining with BAO that probes a later stage, we start to see some inconsistency, and probably there we definitely could try to fit different models, but yeah, still this inconsistency make us a bit uncomfortable to drive strong conclusions in this kind of combinations.
Thank you.
Thank you. Any other questions? Yes, Walid?
Thank you, Federica, for the nice talk. I just want to ask about something related to slide 26, I think.
26, let's go
yeah,
there.
I think it's about temperature to polarization leakage.
Yes.
Yeah. Okay. This is, I think it's a typical issue was studied in Planck before to correct these systematics. So why didn't, my question, why didn't you use try to fix this before unblinding? Yeah, this is my question. Yeah.
Yeah, and this is a good and fair question. So right now, I don't have on top of my head what was done for Planck, but I can clearly tell you what we did here. So we actually didn't know so far that SPT-3G data were affected by this kind of systematic. We actually correct for temperature to polarization leakage monopole at the map level, and this is done before doing this power spectra. What we didn't know is that we had such a significant high order quadrupolar temperature to polarization leakage. This was unknown to us in our data set, and we were actually not able to detect this effect from our null tests, because if we would have seen a hint for that in this kind of consistency test that I've shown, we would have for sure tried to look for what was causing it. But these tests were passing. We had no clue at the time that systematic was in the data, but when we unblinded, we actually saw something strange in terms of cosmological parameters and made us wonder about this. And maybe I actually can go to some late slide that I have in the backup here, because this is a very sensitive problem. Indeed, so when we, after unblinded, we started wondering about what was going on some strange feature we were seeing, we started looking at point sources in our maps, polarized point sources. And by stacking them, we got this kind of features. So polarized sources in the sky that we retained for this cross-check were unpolarized. So we basically should have seen nothing here. But we actually see some strong quadrupolar patterns. So we could have seen this before unblinding if we had looked at stack of point sources. And this is something that unfortunately we didn't do before unblinding. And we were able to, we thought about it only after. And actually, maybe you could be interested in looking at this plot here, and this is how this systematic effect projects to power spectra. And actually, the fact, because we didn't see this effect in our consistency test, is that this is this projection in the bump powers of the quadrupolar temperature to polarization leakage is pretty similar across frequency. You can see, for instance, that at TE 90 and 150, this T2P template is basically the same. And most of our null tests are based on frequency differences. So this similar systematic was basically canceling in our null test. And this is why we didn't spot it before.
Okay, thank you. I think it is clear now.
We can thank Federica Guidi. Thank you so much for everything.
Thank you very much. It was a pleasure to stay here with you this afternoon, presenting these results.